So in day 3, sir is going to talk about basics of magnetic recording. So we will have 2 lectures before lunch. Post lunch there will be a tutorial session. Maybe one of our student will take care of that, and maybe we can schedule a visit to CIR. Is that okay, sir?
Yeah.
So maybe immediately after that tutorial we will have a visit to CIR. So just today we have 2 lectures by process and print. So sir.
Okay, thank you. Okay, good morning everyone. So please log in to OOCLab. Okay. So let's do some questions to recap what we learned yesterday. Okay. Okay, 50-50. Who is right, majority or minority? Huh? Okay, minority is right, majority is wrong. Okay, the answer is already on the board, right? So yesterday I was teaching about the magnetization reversal mechanism. If you sputter deposit a thin film without any special recipe, then you will end up having multi-domains. So your film will have multi-domains, and in that case you will have domain wall motion reversal mechanism. So this is the correct answer. Okay, next one. Okay, now majority is right. Okay, so when you have nanoparticles, I mean when they are very small, you have single domain. So when you have a single domain, there is no domain wall motion, right? Single domain, there is no domain wall. So domain wall motion cannot happen. So the only answer is coherent rotation or the Stoner-Woolfer reversal mechanism. Okay, the correct answer is 2. Okay, next question. Okay, who is right, majority or minority? Majority is right, okay. The answer is here. So I have mentioned that the reversal field or the anisotropy field is given by this formula, 2Ku over Ms. So if Ms is large, then coercivity is going, the reversal field is going to be small, okay. So this cannot be the answer. So if Ku is large, you will have a large Hk, which means larger reversal field. So 3 is right. Okay, another question for which I don't have book lab question, but I'll ask you orally. Suppose you want to make a recording media that stores the information. So that recorded media, should it have domain wall motion or coherent rotation? Which reversal mechanism you want your recording film should have? How many of you say that the film I make for recording application should have domain wall motion? Okay, raise hand. 1, 2, 3, 4, okay, 5, 6. Okay, how many of you say that the recording media that I make should have the coherent rotation or Stoner-Woolfer reversal mechanism? No one? Okay, so all the others have no clue. When I introduced the reversal mechanism, I gave you these 2 examples, right? So in one case, you place a magnet near a magnetic material, then only the region directly below the magnet gets affected. So this is scenario 1. The scenario 2 is you place a magnet, then like a filter paper spreads ink. So here the region of magnetization spreads via domain wall motion. Okay, so now having described these 2, which one will you prefer for magnetic recording, 1 or 2? How many say 1? Only 1. How many say you want 2? Okay, 2. So 1 favor 1, 2 favor 2, the other have no clue. Okay, when you write on a paper, you want to write information. So you want to pack more information on the paper, right? So you want what type of paper? Filter paper type of paper or the paper that doesn't bloat ink? Second one, right? If you write on a filter paper, then whatever you write is going to look very big. Then you cannot pack more information. Okay? On the other hand, if your paper is good, it doesn't bloat ink, then you write with a sharp tip, then you can write more information in a given area. So in a similar sense, when we are looking for some magnetic film to store information, we don't want this. Okay? So if you try to write some information using a magnet, then that information is going to spread. Okay? We don't want that. We want only the region directly below the magnet to reverse the magnetization, so that you can write small bits. So we need the second thing, okay, the snore, not the domain wall motion. We don't need this for magnetic recording. We need the Stoner-Wohlforth type reversal mechanism, where only the region directly below the magnet reverses. This is what we want for magnetic recording. Okay? So that's how what we learned yesterday, and magnetic recording is going to be linked. Anyway, we'll learn more of those again, and we'll recap all these items. So I mentioned on day one that computing, especially the mainframe computers of 1950s, they used hard disk drives first, then later in the 1980s, 90s, people started using magnetic recording, especially in the form of hard disk drive in desktops. Then later, hard disk drives got into laptops. Then later it got into consumer electronics like iPod, Xbox, and so on. Now people store a lot of information in Facebook, YouTube, and so on. Okay? So there are cloud storage, there are personal storage. Okay? Moving forward, there are many applications. Okay? So you know that now artificial intelligence is coming big, and there are going to be autonomous cars which will sense information from various parts, which will detect what is happening on the road. They will generate a lot of data, so you need something to store them. Okay, then somewhere in 2019, Intel introduced a technology called the True View video technology. So in that technology, what happens is if there is a stadium, so surrounding the stadium, there will be like hundreds of cameras. So 360 degree. So every 10 degree, if you have one camera, you have 36 cameras. Okay. So all of them capture information, and when you play, you have different perspective. Okay. I think in 2023 or somewhere, IPL had this technology. Okay, once I saw a CSK match, so there was this technology shown, but I don't know why they discontinued. Okay, so with this True View technology, you can have information on the sports at different angles. Okay, so you play multiple cameras, and you can choose which camera position you want to show. So all these are going to generate a lot of data, and that's why the magnetic recording is very important. So we need cheap devices that store lots of information, and hard disk drive is the only candidate that can store lots of information at a cheap cost. Okay, so today we are going to learn the basics of magnetic recording. So when I start teaching on the data storage concepts, I always bring some analogy. So if I equate something that you know with magnetic recording, then it's easy to understand what's happening. Okay, let's take a book as the information storage system. So in book, you have stored data, right? So any data storage device or system should have a medium to store information. So when I say medium, it is something that stores the information. Okay, so in the case of book, we use paper to store information. So paper is the one that stores the information. So we call paper as the medium in the case of book. And we should have some ways to write information. So in the case of notebook, you use a pen to write information, and in the case of book, we print information using ink. So we have some ways to write information. and we should also have some ways to sense the information. So in this case, we are using our eyes to sense the information. Okay, so these three are not enough. Okay, so you can write information, read information, sense information, but we should also have some ways to interpret the information. Okay, for example, if I show you something like this, you won't know what is written, even though you can see and sense something here happening here, but you don't understand because you have not been trained. Okay? However, whatever I have written here, you should be able to interpret the information because you have been trained to read English. So, in the case of book, our brain and the training we had helps to interpret the information. Okay? So, in the case of hard disk drive also, we have a medium that stores the information. We look at how we write information, how we sense information, and so on. And there are also some coding and signal processing that's happening inside the hard disk drives that helps to convert the digital. I mean, when we talk about magnetic recording, you'll learn that there is some electrical signals coming. So the electrical signals have to be processed so that the computer understands what's happening. So you have hard disk drive, there is some data stored, then there is read head that sends some electrical signal. But the computer, if the computer doesn't know what signal it is getting, you cannot get meaningful information. So the coding and signal processing aspect of the hard disk drive takes care that the information stored can be understood by the computer. Okay, so let's go into the detail. So I always use this triangle. So whenever you design a data storage system, you should have some ways to write, read, and store the information. Okay. Let's say you have a pile of water. You can write information, but water cannot store information. Okay. As soon as you write, the information will be gone. So storing will not be met by water, right? On the other hand, you can write information on sand. If you go to beach, you write information on sand. It may be able to store for some time, but once the next wave comes, maybe the stored information will be erased. So we need to look at all these three criteria. How do we write information? How do we read information? How do we store information? Whether the system that we design, whether the material we choose, be able to handle all these three aspects. So we should take care. Okay. Here I mentioned that there is coding and signal processing. This is mostly done by mathematicians or electrical engineers, but I understand here most of you are physicists or material scientists. So we will not look at this part. Okay, we will focus on how do we write information, how do we store information, and how do we read information. Okay, so in the case of book, we write with a pen, a pencil, or ink. Then we read with our eyes, and we store information on paper. Okay, so if you take rock carvings, for example, so we write information with some nails or whatsoever, some tools, and we read with our eyes, and we store the information in rocks. Okay. So before we go further, let me ask some questions. Okay, none of them are magnetic recording. Okay, if you take a CD or DVD, for example, so in CD or DVD, so if you read the information using a laser, so you'll have different kind of reflection or whatsoever optical properties that you can use for detecting 1 and 0. Okay, so this is the principle of CDs or DVD. So there is no magnetism here. So it's purely optics and this phase change material that makes CD or DVD. Okay, so you are using heating from laser. That's how you write information. So by laser induced heating, you can go between amorphous and crystalline states, and you use reflectivity to read information, and you use a phase change material to store information. And this one we can skip. And if you take flash memory, that's again semiconductor memory that has nothing to do with magnetism. Okay. So when we talk about magnetic recording, we have a magnetic material. So inside that magnetic material, we can magnetize them in one way or the other, and we store information in magnetic materials. So we use magnetic materials for storing information, and we use an electromagnet for writing information. So we learned about electromagnetism yesterday. So basically you have a coil and you have an electromagnetic core. So when you send a current through this coil, you produce a magnetic field. So that magnetic field will go from this pole to the other pole. So either go straight or it will leak. So you can use one of these fields to write information. And you will use some form of magnetoresistive sensors for reading information. Okay. So magnetic recording uses magnetism in all aspects. For storing, we use magnetic materials. For writing, we use magnetism. For reading also, we use magnetic or spintronic principles for reading information. So this is what we call magnetic recording. Okay, so we'll go through this in detail now. So if you look at the back side of a hard disk drive, it will look something like this, and if you open the other side, it will look something like this. Can you open a hard disk drive and put it back? You can do that, but the hard disk will not work again. Okay. So if you open a hard disk drive, it will look something like this. So you have a disk. Okay, so this disk is the one that stores the information. Okay, so this is what we call recording medium. So I told you in book we have paper. Paper stores the information, and paper is the medium. So in a similar sense, in hard disk drive, this disk is the one that stores the information, and we call that as the recording medium. So I'll keep using the word recording medium for the next 2 days. So when I say recording medium, I am talking about the material that gets deposited on the disk, the one that stores the information. So that's what I am going to call recording medium. Then this small thing that you see here, this is the head. It's called head. So it helps to read and write information. Okay, so you use the electromagnetic head, which is hidden here. So that will help to write information. And there's a magnetoresistive sensor again in the same head that helps to read information. So this head is the one that helps to read and write information. And if you look at the back side of the hard disk drive, you will see some chips like this. Okay, so these chips are the like the brain of the hard disk drive. So you will get some electrical signals from this head that goes into this circuit board. So this will process the information and communicate to the computer in a way the computer can understand. So this is like the translator, mediator. Okay. Suppose I speak Japanese and you cannot understand, someone else has to mediate what I am speaking, right? So in a similar sense, these controllers are the one that converts the electrical signal to some language that the computers can understand. So this is basically how the hard disk drives function. Okay, so again I'll play the same video which I have played before. Okay, so now there's a question. Again, same question, but this time you have multiple choice. You can choose one of the answers. Let's say I give you a piece of material. So one is a piece of iron, another one is magnet. You don't have a thread or something, so you can't hang them. So if you have a thread, you'll be able to hang them. Then it will point to the north, right? Then you can find out whether this piece is a magnet or iron, right? But you don't have anything. So you have to tell me which one is the iron, which one is magnet. Okay, they look identical. By looking, you cannot find out, but one of them is a magnet, another is a piece of iron. So how will you find out? Density varies. So how will you find out? What will you do? Okay, so this will be one of the tutorial question. Okay. But once I teach you, you can understand. Okay. So if you have a magnet generates magnetic field, and the magnetic field is stronger at the poles. Okay, that's what the question before, right? So in that video, you saw that there's a long magnet, and all the tiny magnets, they are not going to the center, they are going to the edges, right? So what it means is that the magnetic field is the strongest at the poles. Okay, so you see the density of lines is basically the intensity of the field. So the field is stronger here, weaker here. Okay. So once you magnetize a magnetic material and when they have some poles, the field is stronger near the poles, and you can use this magnetic field from the poles to read or sense the information. Okay. So in magnetic recording, we magnetize the materials in such a way that you have a north pole up or south pole up, something like that, and we sense the magnetic field to sense information. Okay. So for example, if you look at this video, so I have a pile of magnets, and this is a kind of sensor. So this sensor will light up with a red or green color indicating north or south pole. Okay. So when it sees north pole, for example, it may show red color and it may show green when it sees a south pole. Okay. So now I bring this sensor. So you see green has light up. So this is one type of pole, let's say north, and when you go to the other side, it lights up red, which is if this is north, the other one is south, and you see in between there is no light. Okay. So the field is stronger here, so the sensor can sense the field. Field is weak, it cannot sense anything. Now the field is strong, so it can sense. Okay. So we can use a sensor like this to sense information, and the information is stored in whether the north pole is up or south pole is up. Okay. That is one way to simply say the reading of information. So I told you the hard disk drive was invented in 1956. So from 1956 all the way to 2008, for about 50 plus years, the hard disk drives used a technology called longitudinal magnetic recording technology. Longitudinal means the magnetization is lying in plane. Okay. So it's like a arrangement of magnets parallel to the substrate. Suppose I have a disk, let's say this is the disk on which I am going to store the information. So the magnetic poles will be parallel to the disk. Okay. So they are in the plane, so that's why we call them longitudinal recording. The alternative that we are going to talk about is the perpendicular recording, where the magnetization is going to be perpendicular to the disk surface. Okay, so in longitudinal magnetic recording with the electromagnet, you can orient the magnets in any fashion. So it could be like south, north, north, south, something like this. So you arrange the magnetic polarities in certain way, and when you have magnets arranged in certain way, right, horizontally, when two poles, identical poles face each other, there will be a stray magnetic field. So for example, here you have north and north pole, so there will be a stray magnetic field coming up outside the surface. Here again you have two like poles, south and south poles next to each other. So here the magnetic field will be going into the substrate, into the sample. And when you have like poles next to each other, south, north, there will be no field coming out, no magnetic field here. And again you have north, north, so there will be some magnetic flux. Okay. So when I was first learning this concept in 2020, I couldn't understand why it will happen like this. Okay. But it will be easy to understand if you really play with magnets and sense what is happening. Okay. So in this case, you will see an arrangement of magnets. So magnets are in plane. So what this could mean? Like pole or unlike pole? Unlike poles, right? So unlike poles attract each other. So this region represents unlike poles. How about this one? Like poles. Okay, they are repelling. So I couldn't bring them any closer. Okay, this is the closest distance I can bring them to. Okay, so here we have some like pole, here we have some like pole. How about these two? Are they similar or different? Let us say this is north north, then this one has to be south south. Okay, it cannot be north north. Okay, so now let us play with this again. So I bring the sensor. Will you see a light here? Let us say you see green light here. What will you see here? Okay, let's see. Okay. Okay, I bring the read head. So it's showing green one side. Okay, so you see it was showing green here. Let's say this is north, then this has to be south, right? So south south is facing. So now we have red light. Then when you move here, what you will see? Green light, right? Okay, so when you go there again, you will see red light. Okay. So you see, even though, I mean, here like one of them is north north, another is south south. So you see that the magnetic flux is coming out or going in, but when you keep the like poles next to each other, there is no magnetic flux. Okay. So this is roughly the way the longitudinal magnetic recording is done. Okay. So we call this kind of reading technique as the NRG. Okay, it doesn't matter what NRG means for you. So this one way of reading information. Okay, so what we do in computer, there are clock pulses, right? So we have one window, clock window, another clock window, another window, and so on. So during this clock window, if you see a magnetic flux, then the sensor will produce output voltage. So within this window, there is output voltage, then we call 1. Okay, so the next window, again there is an output voltage, we call this 1. Then during the third window, there is no signal, so we call this as 0. And during the fourth window, again there is some signal, we call it 1. Okay. So this is how we read information, 1, 1, 0, 1. Not we read information, we used to read information. This is very old technology. So in that technology, we rely on this kind of reading technique. Okay, you can also do perpendicular recording. So since 2006, we have this perpendicular recording scheme where the magnets are not horizontal, they are perpendicular to the disk surface. Okay. So here is like you have north pole, you will have some flux coming out, south pole also you will have some flux coming out, and depending on what type of flux is coming out, you can call them 1 or 0. Okay, so this is a very simple way of how we read information. Okay. So now let us move on to understand how we store information or what makes the information stored for a long time. I told you that if you have an old credit card and if you put your credit card with a magnet, you will be able to erase the information, right. On the other hand, if you put a hard disk drive with a magnet, you will not be able to erase the information. So how the information is stable even against external magnetic field, all those properties come from something called energy barrier. Yes, let us say this is north pole, this is south pole. So you have a magnet with the north pole facing up, south pole in the down direction, but you want to flip the magnet. Okay. For example, this is my magnet, initially north pole is up, south pole is down, but I do not want to rotate. Okay. Magnet is still in the same position. but I apply magnetic field in the opposite direction and convert this north pole to south pole, this south pole to north pole. So, I can do that by applying very strong magnetic field. Okay. So, what stops me from flipping the north pole to south and south pole to north is the energy barrier. Okay. So, we learnt about anisotropy yesterday. So, we learnt about the Stoner-Wohlforth reversal mechanism and so on. So, when we talk about hard disk drive, we are interested in Stoner-Wohlforth reversal mechanism or the coherent rotation. We are not interested in the domain wall motion. Okay. We are not interested. We are interested in this case where you have tiny regions, single domain particles, and they reverse independent of each other. Okay. So, we are interested in this case. So, in this case I told you that there is a HK. If you have a particle, the particle will undergo a reversal from one direction to the other direction at a field given by HK. So, this is in the easy direction, and in the hard direction the hysteresis loop will look like this. So, you notice that this should be somewhere here. So, in the hard direction remanence is 0. Whereas, in the easy direction you have a large remanence. Okay. So, it switches at HK. All these things we learnt. Okay. So, I also told you that this HK is equal to 2 Ku over Ms, where this Ku is called anisotropy constant, or anisotropy energy density. Okay. So, what it means is that if you multiply this Ku so, when we talk about density of materials, right. So, when you multiply density by volume, you get mass, right. So, in a similar sense, if you multiply this anisotropy energy density by volume, you will get some energy. Okay. This is anisotropy energy density. So, if you multiply the anisotropy energy density by volume, then you will get anisotropy energy. Okay. So, this anisotropy energy is the one that helps to retain the information. So, if this energy is very large, then you will have a hard magnetic material. If this energy is very small, then you will have a soft magnetic material. Okay. So, this is the energy that you need I mean, you have to overcome this energy to make the north pole to south pole and south pole to north pole. So, if you want to change the polarity, so let us say I have a magnet. So, my north pole is here, south pole is here. I do not want to flip the magnet, but I want to apply a magnetic field and change the polarity to south north. Okay. So, without flipping the magnet, just by applying a strong magnetic field, I can change the polarity from north to south, south to north. Okay. So, how much field you require to do this change depends on the anisotropy energy. Okay. So, if the anisotropy energy is large, you need very large magnetic field to flip. If the anisotropy is very small, then you can flip the pole with very small magnetic field. Okay. So, this KUV is called anisotropy energy, or you can also use the word energy barrier. Okay. So, this energy barrier is the one that resists the flipping of magnetization from one to the other. Okay. So, let us take two examples: neodymium iron boron iron. So, which one has a high energy barrier out of the two materials that I have written? Huh? Yeah, let us hear from them. Which one has the high energy barrier? So, which one is the permanent magnet? Iron or neodymium and boron? Neodymium and boron, right? So, which one has the large energy barrier? NdFeB. Okay. So, this is a hard magnetic material. This is a soft material. So, I told you hard magnetic materials have a very large anisotropy energy. Soft magnetic material has less anisotropy energy. Anisotropy energy, energy barrier all mean the same thing. Okay. So, to flip the magnetic poles of neodymium iron boron, you need a very large magnetic field. So, typically you will need around 3 Tesla or more to change the polarity of neodymium iron boron, whereas in the case of iron you just need maybe 0.003 Tesla, something like that. Okay. So, with very small magnetic field you can change the polarity of a piece of iron. On the other hand, if you want to reverse the polarity of neodymium and boron, you need very large magnetic field. Okay, so, this energy barrier is the one that helps to retain the information. So, once we write information on the hard disk drive, the hard disk drive has to store the information, right. So, this energy barrier is the one that helps to retain the information. So, the energy barrier UV is all related to the coercivity. So, yesterday we learnt about hysteresis loop, and the hysteresis loop we learnt coercivity. These are all related. So, if you take an isolated particle, then coercivity is same as Hk, but when you have a group of particles, then Hc will be usually much smaller than Hk. So, the coercivity is somehow an indicator of the energy barrier. Usually when coercivity is large, the energy barrier is large. Okay. Okay, so the analogy to this is, let's say you have a ball inside the bottom of this bucket and you want to transport this ball from here to here, right? Then you need to lift the ball, so you have to change, you have to spend some energy to overcome the gravitational potential energy. Only then you can transfer the ball from this side to the other side. So similarly, if you have magnetization pointing in certain direction, you want to flip the magnetization, you have to overcome this energy barrier. Okay. So this energy barrier is the one that helps to store or retain the information. Okay, so how many of you know the terms volatile, non-volatile? Okay, you know, okay. Okay. So volatile means if you take DRAM, SRAM, there is information stored in those memory. If you switch off the power, the information will be lost. Okay, so DRAM, SRAM, they are all volatile memory. On the other hand, you have the flash memory, or USB device, hard disk, all this belong to this non-volatile storage or memory technique. Okay, that means even if you switch off the power, the information is still retained. So the information is stored in the magnetic recording because of this energy barrier that we have. Okay. So we briefly learnt about how do we read information, how do we store information. The next one is how do we write information. Okay. So writing in hard disk drive is done with an electromagnet. So we learned on day 2 yesterday. We learned that if you have a coil and if you insert a ferromagnetic material inside, you can produce a large field. So this is a blown up version of a writer in hard disk drive, you can say. Okay, so we have a coil, then inside we have inserted some ferromagnetic material. So if I send some current through this coil, there will be a magnetic field, and if I zoom, it will look something like this. So you have one pole here, another pole here. So if I bring a Hall probe for reading the magnetic field, I can see what's happening. Okay, so here there is a video. So when I haven't applied power, it's showing 0.007 millitesla. Okay, now almost 0, but once I apply power, you see it's going to 0.227 millitesla. Okay, so once I send a current through this coil, it produces a magnetic field, and in this case, the magnetic field will go from one pole to the other pole. Okay, it will go this way. So I am reading the magnetic field here. So you see, by sending some current through the coil, we can produce magnetic field. So with this magnetic field, we can write information. So with that magnetic field, you can flip the direction from north to south. Okay, that's what we do. So writing is carried out using an electromagnet. So what happens when you write information is shown in this picture. So this is what we call energy landscape. Okay, so the energy of the system looks like this. So here we are looking at a particle. Okay, so we represent the particle's magnetization by this ball kind of thing. So initially the magnetization is pointing up. Okay, let's say we apply a magnetic field in the opposite direction. Okay, so now the magnetization is pointing up. Okay, pointing up, I am applying magnetic field in the opposite direction. Okay, then this configuration will become unstable. Okay, the energy of the system keeps going up. So at one point of time, you can notice that the energy barrier vanishes. Then the system will go from this unstable state to the stable position, which means the particle will switch from magnetization up to magnetization down. Okay, so this is what happens when we write information. This is a schematic. Yes. So, by increasing the magnitude of the applied magnetic field in the opposite direction. So, for example, I showed you, right, if north is up, south is down, you want to make north pointing down, then you have to apply magnetic field in the opposite direction, and it has to be sufficiently large enough to overcome the energy barrier. So, if you apply some weak field, maybe you are just reducing the energy barrier, but you are not able to overcome the energy barrier. So, this applied field has to be larger than the energy barrier, only then we can switch the magnetization. Okay. So, this is how we write information. Okay. So, the reading, writing and the storing of information in hard disk drive is all related to the concepts that we learned yesterday. So, yesterday I asked you to do an exercise closing your eyes to remember where is MS, where is the MR, where is coercivity and so on. So, all these terms are somehow related to the three properties that we learned: writing, reading and storage. Okay. So, yesterday I did not tell you this term. HS is called saturation field. That means, let us say you magnetize the material to have a large MS, I mean to achieve your MS, then you apply some field, then you can reduce the magnetization to 0. You apply some more field, you can reverse more magnetization, but at some point you will reach the saturation, right. So, that field is called saturation field. So, remember that the x axis is in the x axis is field, y axis is magnetization or magnetic moment. So, whenever we say coercivity or some other field like HN, nucleation field, this is all related to the x axis parameters, and when we say MR, MS, this is all related to y axis parameters. So, the saturation field also is related to the x axis. Okay. So, the field that corresponds to this saturation field, so it is somewhere here. So, this field is called saturation field. Okay. So, this MR, coercivity and HS are related to the reading, storing and writing information. Okay. So, firstly I want to say that the MR determines the signal that we get for reading information. So, rather MR multiplied by thickness. So, you have a magnetic film of certain thickness and that magnetic film has a certain MR. So, if you multiply MR by thickness, you have MRT. So, this MRT determines the signal that you get for reading information. So, the larger MRT, larger signal, smaller the MRT, smaller the signal. Okay. So, the coercivity to some extent shows the ability to retain information. So, I told you that coercivity is related to HK, HK is related to KU, KUV and so on. Okay. So, coercivity is related to the ability to retain information. So, yesterday I also gave you some numbers, right. The magnetic tapes have a coercivity of around 700 Oersted, tapes or credit cards. So, they have a coercivity of around 700 Oersted. On the other hand, the hard disk drives have coercivity of around 6000 Oersted. Okay. So, you know that hard disk drives can retain the information better than the credit card or tapes. Okay. So, to some extent the coercivity shows the ability to retain information. Okay. Then the HS, so what happens when you apply a field as large as HS, you can force all the magnetization in one particular direction. So, in this case Let us say if you go from here to here, when you reach this point, all the magnetization is pointing in one direction. So, we call that as a saturation field. So, Hs indicates how easy or difficult it is to write information. Let us say I have a writing head. So, that writing head can produce 1.5 Tesla. Okay. Then I have two recording media, media A with a Hs of 1 Tesla, media B with a Hs of 7 Tesla. So, which media you can write information easily? First one, right? So, when you have 1.5 Tesla, you can easily write information on media A with the Hs of 1 Tesla. On the other hand, when the Hs is 7 Tesla, you will not be able to write information. Okay. Okay, so this example is particularly useful because in current recording technology, we use media with this kind of saturation field, and our writing heads have this kind of capability. But for future technology, people are looking at something called iron platinum recording media, which have very large Hs. So, in those media you cannot use this writing technology. Okay. So, later I will introduce this again. So, how if your Hs is too high, that means you cannot write information, because we have some limitation in the field produced by the writing head. Mm. Yeah, we will discuss that. Yeah, I mean there is no writing head. Yeah, yeah, but there is some technique. There is some technique people are using. I'll tell you later. Okay, so to some extent, all these hysteresis loop parameters are related to the reading, writing, and the storage aspect of magnetic recording. Okay, let's do some questions. Okay, what is point D? Remnant magnetization. So, I told you that the remnant magnetization is for reading information. Okay, so it's related to reading information. So, 1 is the correct answer. Okay, next one. So, now we are talking about the point C here, this one. Okay, so what is C? Saturation field. So saturation field is related to writability. Okay, so most of you are right. Okay, next question. Point B. Okay, so what is the point B? Coercivity. So coercivity is related to retaining or storing information. So 2 is the correct answer. Most of you are right. Okay, I'll spend a few more minutes, then we will have a break. So I taught you the concept of how do we read information. So I told you that we'll have magnetic flux, and when the sensors go over the magnetic flux line, the sensor will convert magnetic flux information into some electrical signal, and when we have electrical signal within this clock, we call it 1, no signal, then we call it 0, and so on. Okay. So this is very old technology. So at that point of time, we didn't store information at high densities. Okay. So at that, if you remember, Professor Naresh told you that the first ever hard disk drive could store only 5 megabyte with 24 disk of 2 feet diameter. It can store only like 5 megabyte. So earlier days, the density was not high, so we could manage to use these kind of techniques. But as we advance more and more, the bits are highly packed closer to each other. So in the current technology, the bits are spaced at a distance of 12.5 nanometer. So if any of you are making some films and do TEM or something like that, right? So you will notice that your grains are already more than like 12.5 nanometer. Okay. So even if you use 1 grain to store information, that's like 12.5 nanometer. Okay. So these are very, very small bits. Okay. So when you pack very small bits and at very close proximity, so it's not just that the bit is small, the center to center distance also is 12.5. So if you say this is one bit, this is another bit, and this is 12.5, this is 12.5, 12.5, and so on. So if you measure the center to center, it's also 12.5. Okay. So we are packing bits very close to each other. So as a result, the signals that the read heads read will be messy. They will not be like very smooth like I have drawn, right. Here I have shown very clear pulses, but when we store information at such high density, the signals are messy. So the reading is not like what I described. Okay. So the signals are not even digital. So they are so messy, they are like almost analog. So people use a lot of signal processing techniques to convert the analog information to some sort of digital information. So there is a lot of signal processing going on to make meaning out of the noisy signals. So these days researchers are even trying to use artificial intelligence to convert the noisy information into the correct information. Okay, so with that we will have a break, and then we will come back and start here. Okay, we will have break now.